Alright. Use a 0.025 significance level to test the claim that peanut candies have weights that vary more than plain candies. So we want to see if we can test the claim made that peanut candies have weight that vary more than plain candies. The standard deviation for weights of plain candies is 0.051. A sample of 51 peanut candies have weights with a standard deviation of 0.038. Okay. So we are gonna look at our claim. Claim is that peanut candies have weight that varies more than plain candies. And by that we mean that we're talking about the standard deviation. So the standard deviation for the plain candy is 0.051. We're going to let our sigma equal to the standard deviation for the peanut candies. And our claim is that the standard deviation for the peanut candies varies more than plain candies. Since plain candies is 0.051, the claim is that it varies more than 0.051. Okay, and so the opposite of that would be it varies less than or equal to 0.051. And again, this stands for the standard deviation for the peanut candies. So our hypothesis would be that the null hypothesis is the variation is the same or less than the plain candies. Our claim is that it varies more than the plain candies. Okay, so we set up our hypothesis, and the next thing we do is we find the test statistic. So our test statistic, which is chi-square, is found using the sample size minus 1 times s squared divided by sigma squared. From the problem, we know that n equals to 51. We also know that the standard deviation weight for the plain candies is 0.051. So that would be our sigma is 0.051. And we also know that from the sample of 51 peanut candies, it has a sample standard deviation of 0.038. So S equals to 0.038. This is a sample because it's from 51 peanuts candies out of a population of a lot. So in order to use this formula, we need to turn these into variance, okay, because these are standard deviation. So take the number that you have there and just square them, and that gives you the variance, which is 0.0026. So we write sigma square is 0.0026, and then s square can be done using the same way. We're going to go ahead and square them and see what we get. Alright, so if I square those, I'm going to get 0.038. Oh, I'm sorry, just 0.38, not 0.038. 0.38. So we take 0.38, we square, and we get 0.1444. So 0.144 and 4. Okay? So go back here, and we're going to plug these numbers in here and calculate what the test statistic is. Now, this is 51 minus 1, so that's going to be 50. Okay. S squared is 0.144 and 4. Sigma squared is 0.0026. That's right here. Plug it in, use a calculator, and figure out what the chi-square is. 50 times 0.1444 divide that by 0.0026, we get 2,776.92. All right. The next step is to find the p-value so that we can write a conclusion. So here's step 1. Here is step 2. And then we move on to step 3, which is the p-value. To find the p-value, start by sketching a chi-square distribution, which will look like that. 2,776.92. Remember that the graph starts at 0 and then it goes up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then all the way up to down here, which we want that to be 2,776.92. When you look up the table, you're going to get an area to the right. And because we're looking at a right tail, that is also going to be our p-value as well. And if you look at it, it's actually really small, right? So when you look it up, hopefully you'll get a very small number. Now, when we look it up to find our p-value, we also need to consider the degree of freedom. And that is 1 less than your sample size. So you're looking at 50 because your sample size is 51. So the degree of freedom is 50. So let's look that up, starting with the degree of freedom. So start here. Okay, make sure you turn to the last page. This is called the chi-square. It's on the last page. You start with 50, your degree of freedom, and then you underline these numbers. And it's basically you're looking for the number 2,776.92. 27, 29, 32, 34, 37, 63, 67, 71. So the number are getting bigger and bigger and bigger. Your value, which is 2,776, would have to be all the way over here, all right, which is beyond this table. But we don't really need to know the exact area, because the further you go to the right, the area gets smaller and smaller and smaller. So I know for sure that my p-value, which correspond to our test statistic, will be smaller than this. But for the sake of simplicity, we're just going to say that the p-value equals to that. All right? So we know the p-value is less than 0.005. But for the sake of simplicity, we're just going to assume that equals to 0.005. But either way, so p-value is less than alpha. Remember what alpha was? Alpha was your significant level, which is 0.025. This is clearly less than that. So the p-value is less than alpha. Now we conclude that we reject the null that the standard deviation or the variation of peanut candies is less than plain candies. So we're rejecting this, we're rejecting this, we're rejecting this, which means we're rejecting this, right? Because that came from there. Since we're rejecting this, that means we have enough evidence to support our claim. This was our claim. See, that's our claim. Okay, so there is enough evidence to conclude that peanut candy have weights that vary more than plain candies.